3.2, there will be a lot of solving inequalities, compound inequalities, which means that not only do we get to solve one inequality for one problem, but we get to solve for two, which should make your heart rejoice because you love them so much. So remember the sarcasm, I apologize. Unions are or statements. Intersections are and statements. Well, we'll get into the specifics. So a set is just a bunch of stuff. Math people call the stuff in the set. I'm getting into the nerdiness here, but they call them elements. So if you have something in a set and you want to be a math nerd, call it an element. If you just want to call it stuff, I'm okay with that because that's what I would call it. But elements, okay? So stuff or elements are not listed more than once. If you see that stuff is repeating, let me do this mathematically. If you see an element that repeats, do not list it twice. You need to list it, just don't list it more than once, because if you do on a test, then minus points. There's the math nerdiness part of it. You're seeing these with, this is real numbers, rational numbers, integers, whole numbers, and natural numbers. I suppose you didn't care about those symbols. Mathematics, those mean things, though. This is going to sound weird. This R is for, this is the set of real numbers. Some students say that that's a Q. It's actually another R for rational numbers. No, that's a Q, right? Okay, I have to, why are they using a Q for rational numbers? There's a math. It makes us math people look smarter than we are. I've said that before, right? And why is Z for integers? I have no idea. I honestly have no idea. But yeah, maybe, I don't know. So, for example, if I were to use list or roster method, notice that this is not set builder notation because it doesn't have that X such that stuff, right? So this, shoes, shirts, sandals, socks, smock, and suspenders. Like if I were to define that set, it would be set of things you can wear that start with S. Are there more? Sure, I don't care. I'm just demonstrating a list of values. Okay, so set notation though would be X such that X is something you wear that starts with the letter S. They should tell you if they specifically want you to use set builder notation. Usually set builder notation is good with inequalities like we've seen. If they just give us individual values though, then we want to use just the listing method. But you'll notice that both of these require fancy brackets. So if you need some practice with fancy brackets, you'll see that some of mine suck, but it really is just to open up a set of fancy brackets, S, then a 2. That's fancy enough. And then to close it, it's just a 2, then an S. There you go, fancy brackets. Okay, so there's these other examples of sets. C is a set of things you wear. It is possible to have an empty set. Yeah, if you have an empty set, you can demonstrate it with just an empty pair of fancy brackets. And if you like fancy brackets, use it. If you don't, just does not exist symbol. To indicate that an element is part of a set, use the symbol E. There's more math hieroglyphics. If it's not an element, then you just cross it out like this, kind of like you would an equal sign. So example 5 is an element of set G. That's how this reads. 5 is an element of set G. All right, so negative 10 is not an element of set W. I don't think you guys will ever have to use this stuff, so if you're getting nervous about it, don't worry about it. It's just some of the technicalities if you do see them. Now you can read the math, and you can impress people, and like all other math people, you can make people think that you're smarter than you actually are. Our or statements. Or statements. Now, if you see a union, it's asking you to find the values of, or let me rephrase that, it's asking you to find the values of all the sets. So if it belongs to set A, for example, it's part of the union as well, okay? If it's part of just set B, it's part of the union. If it's part of set A and B, it's still part of the union because it's part of all, or at least one of them. It just has to be part of one of them. So all numbers of both sets, but again, if you see that they've repeated in both set A and B, just please don't list them twice. So it says a set of all elements. It's just elements, that's just the stuff, okay? Okay, for this one we have sets A and B. So I'm going to set up my my set A or B. And remember, when setting up these lists, we're going to have to use fancy brackets. So I just put an S and then a 2 together to open it up. And then I go through my list, right? So I go through both sets, and I see right off the bat I've got a 1 in both sets. Now, again, I see it twice, but I'm only going to list it once in the A or B set. So remember, we do not list repeats. Then I see I got a 2, and I am doing these in order. I believe the assignment wants these in order, but I forget. I see a 3. Again, I see a set of 5s, but I'm only going to put it once. I don't see a 6, but I see a 7 there from set B. Then we got 8s and a 9. And then a 10 in set B, 11 in set B, a 12 in set A, and then a 16 in set B, then a 19 in set B, and then finally I see a 20 in set A. So that's all the elements of set A or B, which is exactly how this reads, set A or B. And so I'm going to close this off with some fancy brackets. So I got a 2, then an S, boom, fancy brackets. Now you'll notice I was crossing those out as I went through just because it's easier for me to do it that way so that I can keep track of what values I've used. That way I don't miss any, which I tend to do if I don't cross those out. I think that'll make more sense with this example. So let S be the universal set where S equals, and we could assume that this this would be a continuous pattern. So 1, 2, 3, 4, 5, 6, and so forth, which means we're not including fractional values or decimal values there. So let sets A and B be subsets of S. They probably should have included C there, where set A is these 4 values, B is all these, and then C is all these. If I want to list the elements of set A or B or C, as long as it's part of one, it's part of the full union. Okay, so I've got my fancy bracket set up. I'm just going to list them. So no need for set builder notation, just because it's not really using a inequality here. Now you could say I'm going to do this from least to greatest. I believe that the assignment does want that. So, well, here we go. The lowest value I see is 3. So I'm going to list the 3 first. The next one I see is the 6. Then 8. Looks like, then 9. Don't see any 10s. I do see a 12. No 11s. 13 right there. Hopefully I got enough space. We got 3 14s. That doesn't matter. I'm just going to list it once. And yeah, we got 3 15s as well, so I got to list that just once. Next is 16, 18, 21 it looks like. 23, 24, 25, I guess 26, 30. Now, I was crossing those out just to kind of keep track of all the values that were used, and I don't see any that are not crossed out. Yeah, that should be it. So that's kind of a long list. I don't think you'll see anything like that on the assignment or test. I made that long on purpose just to emphasize, as long as it's part of one, it's part of all, or the set of the union. So it looks like on the assignment, if it's some kind of empty set, they'll probably have you enter DNE instead of the empty set or the doesn't exist one. All right, if we see the intersection of sets, that's the and statement. That means in order for it to be listed in this set, the intersection, it has to be part of all of the sets that are being listed, okay? So if it said it wanted A, this reads, by the way, it's A and B, or the intersection of A and B, then we have to find matches in them. Okay, if they don't match, like if I saw that one was in A but not in B, it's not in the set of A and B. But if I saw A had the number 3 and B had the number 3, it's in this and or intersection set. So, but again, don't list them more than once if you see them. Okay, so we have the sets A and B. This wants the elements of set A and B. That's how that reads right there. Set A and B. This little upside down U there is the intersection symbol. So I am now looking for elements that are part of both sets A and B. So again, I'm starting this out with some fancy brackets. Just going through here, I first see that I've got a 1. And again, it has to match in both, right? So I list it, but I only list it once. Okay. And then it looks like 2 doesn't work, 3 doesn't work, but I do have 5s that do work. So I will list a 5 there in the set. I don't see any 7s. Yep, I do see a set of 8s there as well. So I'm going to put 8 in the set. I don't see any 9s that match, 12s or 20s. And so even though that set B has different numbers, 11, 16, 19, or 10, I went through all of set A, so I don't really care if set B has any other elements. There's no other matches. So now that I have it, there's only 3 elements in set A and B. And so I can close this off with my fancy brackets, but only 3 elements, and that's okay. So here we go. We got sets A, B, and C, but we want the list of the elements A and B and C. So again, this is showing 3 sets, so it has to be not just in 2 or 1, it has to be in all 3. But I have to set up my fancy brackets. Boom, so that starts us out. That's an S and a 2. Okay, so let's scan this, see if we can find some values that match in all of them. I'm actually just going to scan through set A, because if it's not in set A, then it doesn't matter if it's in set B and or C. So starting with 13, I don't see any 13s in B, so I don't have to check C. I do see a 14 in set A, B, and C, though. So 14 would be included of set A and B and C. So there it is. Okay, that 15, yeah, that should work. 15, 15. It's in all 3 sets, so I'm going to list it here in the set of A and B and C. 16 is not in these ones, so I don't really care because A is the smallest set. So I don't care if these, like the 3s match right there. It's not in set A as well, so it can't be listed in the full set of all 3 sets, or the AND set, the intersection set of all 3. So it's just these 2 elements. 14 and 15 with fancy brackets. All right, interval notation we've seen. It shows ranges of a solution for an inequality. But yeah, we are using parentheses sometimes, so I'll reiterate this. Just don't get those confused with ordered pairs. Do remember, though, that if it uses the parentheses, that means that those endpoints are not included. When I use interval notation, I do like to use a graph. Not all students do or need to, and that's fine. But I'm going to use the graph just as a visual representation. It helps me to put these intervals together. If a value is included, we'll have to use the square brackets. So yeah, values can go from negative infinity to positive infinity. We've seen that before. But since positive and negative infinity are not definable mathematically speaking, we can't include those. So if we see negative or positive infinity, we automatically have to use parentheses with those values. All right, so express this inequality in interval notation. So again, I like to see the number line here. To the left, I've got -3. I'm going to put the 0 in there, and then 6 would be something like this. So in comparison with just the -3, right? And you could even write this separately. You could say, well, -3 is less than or equal to x, and not worry about the 6, which may break this down into smaller, more manageable parts. And if that's you and it helps you, do it. If you don't need it, don't worry about it. But right off the bat here, I see that this it could equal the -3. So at the -3, I'd have a closed circle there. That's not a very good one, but it still works. And that one's eating the x. Now, since this is a compound inequality, meaning we're also comparing x with 6, I'm just going to make this a small line showing it goes to the right, and because I want to see what happens with the 6. So the other part of that compound inequality was x is less than 6. So at 6, x cannot equal 6, so it'd be an open circle, which I can do a little bit better there. That one is not eating the x, so it goes to the left. So this means, and this inequality, by the way, was saying that x is everything between as well. So really what we just want is just one line between, like this. So it doesn't matter that the red inequality goes past this because it's limited at 6 through this purple inequality, or that the purple line would go to the left of -3 because -3 is the limit or the minimum based on the first part of the inequality. In fact, to emphasize that too, just think about values you could replace with x with to make this true. I mean, 0's at least with a graph. 0 is hopefully an obvious one, but 1 would work, 2, 3, 4, 5, or even like -2 or -1. All of those would work in between. But if I come over here and I say, well, I'm going to replace x with -4, it does make this part true, but it has to make both of them true. Since it's it has to make both of them true. This actually ends up being an intersection or and statement if you were to list these separately, but they do like to see these as full compound inequalities like this. Oh, I almost forgot to put this in interval notation. So starting at -3, which is included, so that'd be a square bracket, and then this would go all the way to 6, which is not included, so that would be in parentheses. That is the interval. Now again, I use the graph to do that. Not everyone does, and that's okay too. You know, that's a good point. So if the closed circles are going to force the square brackets, yeah, and then the open one, yeah, the parentheses, yep. All right, we want to find the union as a single interval. How do we know it's a union? Because they got a U right there. As a single interval. Well, this, again, to me, I think this will make better sense on the graph. So let's have a bigger graph than that, though. Okay, so let's do this first one here, -10 to -1. I got to keep track of this perhaps a little bit better. I'm going to put 0 here. We'll put -10 there, and then -1 here. So at -10, that I see a square bracket. That's a closed circle at -10, and then a parentheses at -1. That'd be an open circle at -1. Okay, and then it's everything between. So that red line with the 2 endpoints represents that interval. Now, we've got this one. I'll do it in purple. -7 would be, we'll say, about right here. And then 3 about right here. Okay, now at -7, there would be a closed circle, because it is a square bracket. 3 is a parentheses, so I'd have an open circle at 3, and then everything in between is included. Now remember, a union, it only has to be part of one for it to make the actual union true, which means actually what I'm looking at here is the minimum here is -10. Okay, so I would have to start the union at -10, which is included, so I'd have to use a square bracket there. So starting at -10, I can see this goes, it doesn't stop at -1 because the purple line continues that on to +3. So at +3, which is the other endpoint, it's an open circle, so I'd have parentheses. This right here is the single interval that represents this union. Now, let's say that it had the intersection symbol in between, then it would have to be between the -7 and the -1. Well, I think we'll see an example like that. Yeah, there it is. So this one, we need some kind of intersection between these two intervals. Why is this the intersection symbol? I have no idea. But try to convince yourself to feel good about it. Or never do, I don't know. Okay, so let's do this first one. Again, I'll do it in red. So we do like to see 0 there, which is part of the second interval. But either way, I have a -5 here on the left of 0. That is a square bracket, so that'd be a closed circle there. And this one, it's going to go all the way to infinity. So this line would just roll all the way over. And that represents that first interval. The next one, starting at 0, so that'd be a closed circle because it's a square bracket. And yeah, this one also goes to infinity. So this one, hopefully you can see those two colors there okay. This one also goes all the way to infinity, but we want the intersection, which means on a graph for me, I'm just looking for where they're stacked. So I can see if I go all the way to the left, starting at -5, it's not stacked until I get to 0. Okay, so 0 would be kind of my lower limit here. And it's not only part of the red, but it's also part of the purple, so it's included in both. So it's also included in the intersection. From there, everything goes to the right all the way to infinity, which is never included. So this interval is the intersection of these two intervals. Be careful, because some students are like, well, it goes to -5 though. No, the red one does, but not both. It has to be both. All right, solving inequalities. I think we've seen this slide before. Just remember, we're using principles of equality. Whatever you do to one side, you got to do the other side, just with one exception. If you ever use multiplication or division principles of equality with a negative, meaning you divide both sides by a negative, multiply both sides by a negative, you have to flip the inequality because the negatives are opposites. So when solving a compound inequality, it may be helpful to split the inequality into two separate inequalities. We probably won't. By compound inequality, I'm talking about full compounds like these types. You can't separate those into two, which we've seen. If it's an or and statement, then they'll already be separated into two inequalities that you'll have to solve. And since we love these so much, it's twice the fun. This one actually is not too bad because it's done. I don't actually have to do any principles of equality to solve this, right? So I'll do this one. I'll do the first one in red. Let's get some numbers on the number line though. So we got 0, 6, and 12. So at 6, that's x is less than 6, so that's an open circle. It's not eating the x, so it goes to the left. And then I'll do this one in purple. That's a 12, but it could be equal to 12. So I got a closed circle of 12. This one is eating the x, so it goes to the right. If for some reason we had an and statement between those two, there wouldn't be any solutions because the two lines never intersect, which we saw in the one example. But for the or statement, I know this goes to negative infinity. It stops at 6, which is not included, so it's a parentheses. I'll unite these two starting at 12, which is included, so it's a square bracket, and it goes to infinity, which is never included. So there's a parentheses. This is the interval that we want. For this or statement, we do need this graph, though. And then, yeah, it's already solved the inequality for us, so that's pretty good. Let's jump to this stuff because it's so fun. And this is an or statement, so as long as it's part of one or the other, we're good, okay? So I'm going to start with this one on the left. I'll solve it in red, and then I'll graph it in red so that we can keep track of what we're doing. I'm going to keep my x's on the left and then the numbers on the right. Now, I'm doing this with a little bit more purpose than just to do this randomly or to just always do it. By putting the x on the left here, it's going to guarantee the coefficient of x to be a positive, and then I will not have to flip the inequality. So in this process, I'd have to zero out that plus 4 by subtracting 4, but if I do it to one side, I got to do the other side. Also, the negative 4x, I'll have to zero that out by adding 4x's to both sides because it's on the numbers side of the line. So that'll zero that out. 4x's plus 4x's is 8x's, and that does not affect the inequality. Negative 4x's plus 4x's, 0. 52 minus 4 is 48. So right here, I'm going to divide both sides by a positive 8. That means the inequality will stay the same. I now have x is less than 6. I'm gonna roll with it on this next one, on the next inequality. But not really that I'm forcing it to happen. It's just going to happen because I'm going to keep that setup the same. So, right? Well, before I do the number line, actually, I should solve the next one, just so I know what values to put on my number line. So let's see what happens here. I'll do this one in purple. I see that I've got some distribution there. So two groups of negative 3x's would be negative 6x's. Two groups of negative 7 is negative 14. No other distribution is required here, so I'll have to drop that. And I think some of you can do this without all these steps. If you can, that's fine. But I got to combine these like terms. Negative 14 plus 6 would be a negative 8. So now I got negative 6x minus 8 greater than or equal to 10x minus 72. Principles of equality here. So I'm just going to stick with x's on the left, numbers on the right. And by doing that, it should force the coefficient to be negative. If you don't want that, then just put your x's on the right. It doesn't matter. So we'll have to add 8 to both sides because the negative 8's on the wrong side. And we'll have to subtract 10x's from both sides because the 10x is on the wrong side. So that'll zero these two parts out. Negative 6x minus 10x would be negative 16x's. Again, addition and subtraction will never change the inequality. And then negative 72 plus 8 is negative 64. Oh, that's convenient. Because next, when I divide both sides by negative 16, and this at this point it's good to notice, we just divided both sides by negative. That now flips the inequality. It's no longer greater than or equal to, it's now less than or equal to. I have a phantom 1x is less than or equal to 4. Okay, so now that I have both those values, I'm ready to graph. I like to see where 0 is on the graph just to help me keep track of where the numbers are getting bigger or smaller. And we're comparing 4 and 6. Now notice I didn't put any other values on the graph because I'm doing it by hand. I don't really need to. 0 is a nice value to have. So starting with the red inequality, I got x is less than 6. So that'd be an open circle at 6 because it's not equal to 6. And this one's not eating the x, so my red line is going to go to the left. Now I'll do the purple inequality, so that's x is less than or equal to 4, so that would be a closed circle at 4. But it's not eating the x, so that goes to the left as well. All right. Now this is an or statement, which means that the purple line that I have here is already part of the red one. So it's included in the red inequality, which means that really the only inequality I needed was this one. We actually don't need this one. In fact, the purple line as well is not really necessary. When you graph this, just graph one line starting at 6, going over to the left. And then last of all, let's make the interval notation here. So I'm graphing the green because that shows the or statement. This goes all the way to negative infinity, which is never included, and then ends at 6, which is also not included. So we have the inequality, which we've boxed in. We don't need the x is less than or equal to 4 because it's included. We have the graph, and then we have the interval. Just as a general rule, usually for or statements, this would usually go this way, but it doesn't always have to, just like we see there. If that were the case, then I'd have to show the interval for the purple, and then the red one would have went this way, and then the red. But I'd have to unite them between. Same idea. Let's start by just solving these. So I'll do this first one in red again. Two groups of negative 6x would be negative 12x's. Two groups of negative 7 is negative 14. Nothing else. There was no other distribution there, so I'm just dropping the rest. Combining like terms, negative 14 plus 2 is negative 12. So I now have negative 12x minus 12. And that's greater than or equal to negative 10x minus 28. Principles of equality. Now I'm going to do this one with some purpose. So I'm going to put the x's on the right, just so that my coefficient of x is a positive, and I won't have to worry about flipping the inequality. Plus, it's good to see that you can if you want to. So my number is going to be on the left. That means the negative 12x is on the wrong side. I have to zero that out by adding 12x's to both sides. And also the negative 28 on the right, that has to be zeroed out by adding 28 to both sides. So that zeroes out these, and then the 28s. Negative 12 plus 28 is positive 16. Again, addition and subtraction principles of equality do not affect the inequality itself. Negative 10x's plus 12x's. See this? Just by choosing that the right side of the inequality forced that coefficient to be positive. So now, at this point, when I look to divide both sides by 2, I don't have to worry about flipping the inequality. Do you have to do it that way? Of course not. But now I have 8 is greater than or equal to x. And again, just like we did on the last problem, before I graph that, let's see what the next one produces for us. And we're still in an or statement. So this one, I'm going to put the x's on the left, numbers on the right. Why am I doing that? Because again, my focus for this problem is to force the coefficients to be positive so we don't have to worry about flipping the inequality. So the negative 2 has to zero out by adding 2 to both sides. And then also the negative 2x is on the number side of things, so I have to zero that out by adding 2x, but to both sides. So that zeroes out, whoops, these terms. 4x's plus 2x's is 6x's, which is now greater than 28 plus 2 is 30. That's nice. These are coming out very pretty, but you probably should expect some fractions or decimals on the assignment. So now x is greater than 5. Okay, now this is an or statement. If I need the inequalities, I would probably put an or. You should put an or statement there, okay? So if you ever get an or statement that's going to work, and I don't know if this one will, possibly, no, I think we should only need one for this one. But if they're ever separate, make sure you put an or statement between the inequalities like this, because we need one for the interval as well, if it's needed. All right, so 0 would be over here. I'll put 5 here, and then 8 is to the right of 5. So starting with the red one, that's 8 is greater than or equal to x. So that is a closed circle at 8, because it could equal 8. It's not eating the x, though, so this one goes to the left. And I'll extend that. There we go. Now the next one, x is greater than 5. So at 5, that's an open circle. But this one is eating the x, so this line goes to the right. Okay. We want, it doesn't matter if it's part of one or the other. I can see that this line goes all the way to negative infinity. And then you, over here to negative infinity, just following on the red line, I can see it doesn't actually stop at negative 5 because negative 5, it's not part of the purple one, but it's part of the red one. So I can continue on to the red till I get 8. And then it doesn't stop at 8, though, because I can jump on the purple one, and it goes forever as well. So, yeah, negative infinity to positive infinity for this one. If you were to look at that, you could actually flip it and say, well, x and 8. Remember that it's eating the 8, though, so just make sure that you can flip it this way. So if, like I did this strictly to make the coefficient a positive up here with the 2. But yeah, if you get confused by that, feel free to just flip it back around. Just make sure it's eating the correct direction. Yeah, the other thing about this is the graph. If you were to graph this, you don't want the circles here or here. What you're going to do, because you should do this by hand, is you're going to click on the left and then drag it all the way over to the right. The green line is actually the real graph that you would need on the assignment because it's everywhere. It doesn't stop at 5. It doesn't stop at 8. The or statement tells us it's all of those values. Yeah, I think this is where we would say, instead of the inequality, we would probably just write something like all real numbers. I could be wrong there, but I forget what the assignment says. I apologize. Now we have our and statement. The one on the right, for some reason, is much bigger than the one on the left. It doesn't matter. It's just more work, not really harder work, hopefully. So this one, I'm just going to stick with keeping the x's on the left, numbers on the right. Some of these coefficients could be negative. I don't care, because we can work with negative coefficients. So I see that my x is on the left. I got to get rid of that minus 8, so add 8 to both sides. But also the 5x, it's on the number side of things, so I'm going to subtract 5x's from both sides. So the inequality won't change. It's going to zero out these terms. 8x's minus 5x's is 3x's. Negative 5 plus 8 is positive 3. And then to solve this one, we're dividing both sides by positive 3. That's why that inequality stays the same. X is now less than 1. And, well, let's see what we get out of the second one. Oh, it's, yeah, we got this distribution. So two groups of negative 8x's first would be negative 16x's. Two groups of negative 1 would be negative 2. The rest of that inequality stays the same. No other distribution necessary. So combining like terms, negative 2 plus 6 would be positive 4. So now negative 16x plus 4. And then we still got the rest of that. And again, I'm going to keep the x's on the left, numbers on the right. So we'll have to zero out that plus 4, so minus 4 from both sides. And also add 4x to both sides. Right, that zeroes out these terms, which is what we want. Negative 16x's plus 4x's is negative 12x's, which is less than or equal to 64 minus 4 is 60. Yeah, it's going to give us a nice even answer, because now when I divide both sides by negative 12, I divide both sides by negative, which means that inequality will flip. X is now greater than or equal to negative 5. Okay, so we got these two inequalities. I've got the and statement. Let's see what the graph looks like, and then we'll see if we need to finalize that inequality there. So we got, I put 0 here. I got negative 5 and 1, something like this. Let's start with the red one. X is less than 1. So at 1, I've got an open circle because it's not equal to 1, and it's not eating the x, so the line will go to the left. I'm not extending this line because I'm looking for stacked lines, right? So let's see what the negative 5 does first. X is greater than or equal to negative 5, so at negative 5. Yeah, after we see what happens with the purple line, we'll see how this affects the red line. But this one, it's eating the x, the purple one, so this line is going to go to the left. So I'm looking for where the lines would be stacked. So this means that the purple line, it would go all the way to 1, and then the red line would go, the inequality says that it goes beyond that, But since I need the intersection of the two, they intersect between these 2 points. So even though the red line goes to the left, the purple line goes to the right, neither of those matter because I need the intersection. So really we're just looking for this right here. So on the assignment, you'd put a closed circle at -5 and then an open circle at 1, and then you just drag the line between to make that full line right there. But again, don't go beyond those because we want the intersection only. So that's the graph. Next, we want the interval notation, yeah. So starting at -5, which is included because it's a closed circle, and then this goes all the way to 1, which is not included, so that's a parentheses. Okay, so we got the graph, we got the interval. What we need now is to actually redo the inequality, okay? Because I can see, let's compare it with purple, right? So if I were to change this, I'd have, why am I starting with purple? Because it's the lower value. -5 is less than the red one. So I'm going to change this so that I can set this in a compound, one individual compound inequality, which I believe they want on the assignment. So with comparing this with -5, it's a less than or equal to, because it needs the x, but it's also equal. And then I can see from the red one, I can compare x with 1 there as well. So from what I remember, I think they want this one. To me, the and statement is good enough, but you need that there, right? X is less than 1 and -5 is less than or equal to x. To me, that would be good enough, but I think on the assignment, they need that one right there. And yeah, like I said, I would probably leave it like this just because I don't like to do this extra work. But this one is more formal and it's more compact. It's maybe considered simplified. Okay, let's do these ones, 2-steppers on these. So let's solve this one, add 3 to both sides. It zeroes that out, drop your 4x, which is less than -20 now. And then divide both sides by 4. So x, again, that did not flip the inequality because we divided by a positive, but x is less than -5. And, so I'm going to put the and statement there just so I don't forget. Principle of equality, we'll add 7 to both sides. So drop the -3x. -7 plus 7 zeroes out. -13 plus 7 is -6. Here we're going to divide both sides by -3. So that will flip the inequality. And x is now greater than or equal to +3. Oh, dang it. I was so close.
Just off by 1.
But I was an infinite number of decimals away. That's thank you. Okay, so we have the inequalities. Let's go ahead and make the graph then. I'll put -5 over here, 0 there, and 2 there. Again, it doesn't have to be proportional exactly. So at -5, I got an open circle there. And this one's not eating the x, so it goes to the left. That should make us suspicious with an and statement, but let's see what it does with the purple. So at 2, I got a closed circle. And this one is eating the x. Yeah, so this one, it's going to the right. So we have to ask ourselves the question, where do these 2 lines intersect? And again, that's because it's an and statement. And the answer is they don't. So that tells us that this one just has no solutions. On the assignment, I believe it's a D&E situation. I think the interval as well, I think if it asks for that, you just type in D&E. The graph, I don't think that asks for a graph on this one. I could be wrong. But I don't think you'd put anything on the graph because nothing on the graph is true in an and statement set. So yeah, even the interval here, it's a D&E situation. Well, let's write this inequality. I'm going to start with this line here to the left. I'll zoom back out, but I just want to focus on one at a time, which means I don't really care about this one for now. So I can see right here, we'll do this one in red. It's got the arrow, so that means it's going to go forever to -infinity. It does stop, though, at -2, which is an open circle, so that's going to be a parentheses right there. Okay, so I have that one. Let's go to the next one here. This next one, it starts at -1, which is not included because it's an open circle, and then it goes all the way to 1, which is also not included. So it's a parentheses. So now looking at the whole thing, since I guess we get to assume that all of these are true, even though they didn't tell us, we'll have to unite those two intervals with a U statement or an OR statement.